Welcome to Let's Get to the Marks. I'm going through a physics and maths tutor pack. Once again, that is an awesome site. Everyone should know it if you're revising for A-level. And I'm just going to walk you through some of the questions on physics and maths tutor. This is my carboxylic acids and their derivatives, part 3. And we're starting with question 6. So here we have make sure you pause the video, by the way, and then have a go on some scrap paper that you can chuck away after. So we've got some sort of reactant. In step 1, it's split into two different things, an alcohol and ethanoic acid. Then we've got a halogenoalkane at the end of step 2, and then an unknown compound S, and then we have some sort of amine at the end of step 4. So give the reagent and conditions needed for step 1, show how you'd state how you'd obtain a sample of the alcohol formed from the reaction mixture. So first thing to note is, what is the reactant in step 1? Can you spot anything interesting about this reactant? Well, it's got an ester link. You should be able to recognize that functional group. This is an ester. And so what happens to esters when we break them down into two products? Well, we get an alcohol formed. This looks like butan-2-ol, this alcohol, and we get ethanoic acid. So, well, we don't necessarily get ethanoic acid, we get carboxylic acid. This is a derivative of ethanoic acid over here. We'll talk about its name later on, because I think they ask you its name later on in the question. So what's happened? How do you turn an ester into an alcohol and carboxylic acid? You hydrolyze it. That means you break the bonds and you split it, and it goes back to the two of the reactants the ester itself was formed from. And so we have an alcohol and a carboxylic acid. So it says, state how you'd obtain a sample of the alcohol from the reaction mixture. First of all, give the reagent. Well, look, there's a sodium ion added to the carboxylic acid in the ester. So we'd need sodium hydroxide. This is actually called base hydrolysis because we're using a base. Now, what condition do you use for base hydrolysis? Well, you use reflux. Okay, so that's the method you need to know. Once again, I recommend revision cards. They're absolutely awesome for revising organic chemistry, and the best way to do it. So you'd be like, the question you'd have on the front of the card, you maybe had 3 or 4 questions, but would be something along the lines of, name the reagent and conditions for base hydrolysis of an ester. And so you'd be sodium hydroxide reflux. We'd normally use dilute sodium hydroxide, but it's not on the mark scheme that it has to be dilute. Okay, and then it says here, how would you separate the alcohol? Well, the alcohol is going to be we've got a salt on the right. We don't need to worry about that, but the alcohol needs to be separated from any excess ester. And so you're going to use distillation, or if they've got similar boiling points, you use fractional distillation. And how do you know if something's got a similar boiling point? If it has a similar MR, it's going to have similar strength van der Waals forces, so the boiling points will be similar. Okay, those are your 3 marks. Let's move on and stop all the waffle. Draw the structure of compound S. For each of steps 3 and 4, give a reagent and one condition other than heat. And this is the last part to this question. So let's go to compound S and have a little look. So in order to find out what compound S is, you kind of really need to talk yourself through all of the steps to work out what's going on. And sometimes look past compound S at the final step, because this will also help you. So we're trying to figure out, first of all, what is compound S? Well, it's been formed from a halogenoalkane. So this is the content you need to know in your CGP or your revision guide or your notes, is what can be formed from a halogenoalkane, or a haloalkane as they're sometimes known. Well, if you do nucleophilic substitution of an alcohol, you can see we've got butan-2-ol, you can make 2-bromobutane here. But they're not really asking us about step 2. But this just helps us. Now we look at compound T. What's happened to compound T? Look, there's 4 carbons in the alcohol and 4 carbons in the haloalkane. By the time we get to compound T, we've got 5 carbons. So in step 3, we must be adding a carbon. And the only way to do that is by using a nitrile group. So again, nucleophilic substitution here. We're going to swap that nitrile group for that bromine atom. Okay. And what is going to be a source of nitrile ions? So you should be thinking about that as a reagent for step 3. What's a source of nitrile ions? And what's the formula of compound S going to be? Well, just swap out that bromine for CN. So CH3, CH, CN, CH2, CH3, and that will get you a mark. That's going to be the structure of compound S, because you're going to be swapping the CN where the bromine is. And of course, you've added an extra carbon. So what was the source of the nitrile ions? Hopefully you came up with it. We can use potassium cyanide or sodium cyanide, okay, KCN or NaCN, and you want to dissolve these in ethanol. And the reason why is ethanol is a really good solvent for polar and non-polar substances. So we will have scored our first 2 marks. Now we need to know what's the reagent for 4. So what do you need to go from compound S, which um, to what? How do we get from our nitrile over to our amine over here? So, well, let's think about the bonding. You've got a carbon atom joined to a nitrogen with 3 covalent bonds. We need to wipe out 2 of them, it looks like, and add 2 hydrogens to the N to make the amine, and add 2 hydrogens to the 5th carbon on compound C. So what are you actually adding? Well, you're adding hydrogen, H2. You've got 2 molecules of H2 added here, and you're going to need a platinum or nickel or a palladium catalyst. There's a bunch of other catalysts you can know. I just remember platinum and nickel for this one. So once again, I recommend you writing up a revision card and asking yourself, what is the reagent for this particular reaction, and writing the answers on the back. It's the only way to learn organic chemistry is through revision, memorization. Best to use revision cards. Here are the 3 answers you needed to get the last 3 marks of this 8-mark first question. So that is the structure of compound S. You need KCN and ethanol, and that is for the reagent and condition for step 3. And then the reagent is hydrogen to make the amine, and you need a platinum catalyst. You could say palladium or nickel. There you go. That's the reagent and the condition. Super. Let's move on to the next question. Question 7. Coconut oil contains a triester with 3 identical R groups. The triester reacts with potassium hydroxide. So you can see we've got 3 KOH reacting with a triester in coconut oil. Complete the equation by drawing the structure of the other products of the reaction in the box. Name the type of compound shown by the formula RCOOK. Give 1 use of this type of compound, and that will get us another 3 marks. So first of all, I just want to show you that our 3RCOOK has come off, so we need to remove that from our reactants on the left. Whatever's left over, we just combine to make the product in the box. So we're missing CH2, CH2, and 3 OHs. And of course, this is going to be a molecule of glycerol, or propan 1,2,3 triol, which is the IUPAC name. So you can, this is like a displayed formula I'm showing here, but we can also write out the structural formula, which is probably better for this question. And the next part of the question, we've got name the type of compound shown by the formula RCOOK. So you have to really look at what that is. That is some sort of carboxylate ion, and it's got a potassium, so potassium carboxylate, or we could just call it a potassium salt. Okay, and you get these when you break up an ester with base hydrolysis. And you can see what happens is a positive potassium ion from your source of potassium, like KOH, joins on to the lone pair on the oxygen on the carboxylic acid group, on the carboxylate ion. So you get potassium carboxylate, or a carboxylate salt, or a potassium salt. And the use of these is soap. Okay, so nice, easy 3 marks. Let's move on to part B, which is an amount of substance question. So the triester in coconut oil has a relative molecular mass of 638. In the equation shown at the start of this question, R represents an alkyl group that can be written as CH3CH2N. Deduce the value of N in CH3CH2N. Show your working. So we've been told that the MR is 638. And what we need to zing back up here, check this out, right? we need to find out what R is, right? They're asking us what is R. So the first thing we need to do is subtract all of this from 638. All of the COO and the CH2, CH2. We need to add that all up using our periodic table and our relative atomic masses to create the MR of all the stuff that we need to remove to be left with the 3 R's. Once you're left with the 3 R's, divide by 3 and you've got the MR of R. And then you can work out by a bit further subtraction what the MR of R is. Okay, what the MR of the CH2 section is, and then you can work out what N is. So let's have a little go. First of all, I want to take my 638 and I need to get rid of the kind of the glycerol component here, the CH2, CH2. I need to get rid of that. So let's add that up. So that's 18. And it's not really glycerol because it doesn't have hydroxide ions attached, but it's 18, 13, and 14. So that's a total of 41. I'm going to need to take that off of the 638. And then I've got 3 times CAA. Do you remember we had each of these connected to this structure, which I've given 41 to? Well, a carbon atom has 12, an oxygen, 2 oxygens, are 16 each, 32. So that's 44. And we got 3 of them. So if I add 41 to 3 times 44, I get 173. So I want to rip that all away from the 638. Now, I'm not done yet. Look at what it's asked us to deduce the value of. It's asked us to deduce the value of N. So we just want the CH2 in the brackets. We don't want those CH3s on the side. And each of the R groups starts with a CH3. So what I need to do now is add up CH3, which is 12, plus 3 is 15. And I need to subtract, I've never heard of that word. I need to subtract 3 times 15 as well from the 638 because I need to remove 3 CH3s to just leave me with 3 CH2Ns. So when we do 638 minus 173 minus the 45 for the 3 CH groups, we're going to end up with 420. But remember, the 420 represents 3 R groups or 3 lots of CH2N. I need to just find out what 1 lot of CH2N is. So I'm going to do 420 divided by 3, and that is going to give me 140. So I'm going to get 140 equals 1 lot of CH2N. Now I need to work out what N is. Let's add up how many CH2s go into 140. Well, CH2, carbon's 12, hydrogen's 2, because one hydrogen atom is 1 AR, so total of 14. So divide 140 by 14 and we'll get 10. So N is 10. There are 10 CH2s in each R group. So N is 10. Hope that helps. Make sure you hit the like, you subscribe on all of that. It really helps my channel. And if you leave a comment, YouTube even checks the algorithm and it will get my videos out to more A-level chemistry students. Nice one. Well, let's finish up. We've got another part to go, part C, and it's another amount of substance question. So 1.450 grams sample of coconut oil. So a 1.450 gram sample of coconut oil is heated with 0.421 grams of potassium hydroxide in aqueous ethanol until all the triester is hydrolyzed. So we're going to hydrolyze all of the triester in the coconut oil. The mixture is then cooled. The remaining KOH, some of the KOH is left, obviously, that must be excess, is then neutralized and by exactly 15.65 centimeter of 0.1 mole per decimeter of hydrochloric acid, just flick down to show it's the 6 marker, calculate the percentage by mass of the triester in the coconut oil. So this is really like a back titration because they've hydrolyzed all of the ester with 0.421 grams of KOH, but we've got some of that mass of KOH must be left over. And so what they do in a back titration is they take that leftover KOH and they neutralize that fully with an acid. normally where it has a one-to-one reaction, which it does in this case. So they've used 15.65 centimeter cubed of zero point 0.1 mole per decimeter of hydrochloric acid, and that has neutralized the KOH. So from that, we can work out the moles of hydrochloric acid. As it's a one-to-one ratio with the KOH, we can work out the moles of the KOH. We can subtract that from the original moles of the KOH, which we can work out also, to find out how many moles of KOH reacted with the triester. We can then use the ratio of triester to the original KOH and work out the moles of triester used, the mass of triester, and then the percentage mass in the coconut oil. So you should pause the video right now and have a go with a pen on a scrap bit of paper using all the data and the numbers you've got. Okay, there's several points you could start here. You could start by working out the original moles of KOH from the 0.21 grams. But I'm going to start right at the bottom numbers we've got, which is with the hydrochloric acid. Now, we know that hydrochloric acid reacts in a one-to-one ratio with KOH. Now, how do I know it's one-to-one? Well, I could write the full equation out and balance it. But if you look at potassium hydroxide, there's one hydroxide ion in KOH, and there's one hydrogen ion in hydrochloric acid. So they're going to come together perfectly to make one molecule of H2O. So I know it's a one-to-one between the acid and the alkali, or the base, in this situation. So anyway, let's work out the moles of HCl, and in fact we're working out the moles of KOH that were left over. So we're going to use N over CV, which you should know from your triangle. And we're going to do 15.65 divided by 1,000 times 0.1. And that's going to get us, if we whack that in the calculator, 0.001565 moles of HCl. We know it was one-to-one with the KOH, so which tells us that we got 0.001565 also moles of KOH. And that was the moles of KOH left after it reacted with the triester. So now what I want to do is find out the original moles of KOH that reacted with the triester and minus the ones left over to find out how many moles of KOH actually were used up in the reaction with the triester. So the original moles of KOH at the start was 0.421 divided by 56. That's because the relative atomic mass of potassium is 39, oxygen 16, and hydrogen's 1. So it has an MR of 56. Remember, mass over MR equals moles. We'll find out that we started off with 0.0075 moles of KOH. After the reaction with triester, there were 0.001565 left. So I'm going to do 0.0075 take away 0.001565, and I found out how much KOH was used up with the triester in the hydrolysis. And what we're going to get there is 0.005935 moles of KOH reacted with the triester. Now, if it was a one-to-one reaction with the triester, we'd also have 0.005935 moles of triester that was used up, but it's not a one-to-one reaction. Can you remember from earlier on in the question how many molecules of KOH react with one triester? Remember, it's a 1-to-3 ratio, as in one triester molecule reacts with 3 KOH. Remember, that OH is used to form the glycerol and to break that bond with each of the R groups. So we need to do 0.005935 divided by 3 to find out our moles of triester that we originally had that were completely hydrolyzed. And the answer is 0.0019783 N, or moles of triester. That is how many moles of triester we had. So you've got most of the marks now. We just need to use that M over MR times moles and convert that back to find the mass of triester in that many moles. Remember that the MR was 638 of our triester in the coconut oil. So we need to do MR times moles. So 638 times 0.00197883. And we're going to get a mass of 1.262 whatever that is, 17 grams. And we're going to divide that by the original mass of the coconut oil, because not all of it is triester. So we're going to go 1.26, 217, and divide that by 1.450 grams times 100, and that's your final answer for your percentage by mass of triester in the coconut oil. No, it's always best to keep all, if you're really good with a scientific calculator, the best thing to do is to keep all your numbers in the scientific calculator from the start of your calculation to the end. That way you get closer to the true value that they want in the mark scheme. I got 87.04, so I could just round that to 87%. They accept anywhere from 87 to 87.1%. So there we go. Right, the final part of this question is D. And that is the final part of this walkthrough. I'm going to do another carboxylic acid walkthrough, part 4, pretty soon in the next week. Suggest why aqueous ethanol is a suitable solvent. Okay, so why is ethanol a suitable solvent for this reaction? Well, if you check out triesters, they've got this. We've already found out earlier in the question that there's a CH210 bit, right? CH3, CH210, the R group. And that's going to be fairly non-polar, right? There's no positive and negative elements, delta positive, delta negative there. Yes, we've got the ester bond, which has got some polarized parts. And you've got the alcohol, you've got the, potassium hydroxide, which is obviously a polar molecule as well. So we kind of want a solvent that combine together a non-polar and a polar reactant and mix them together. And what we find is that alcohols have a non-polar bit themselves, i.e. ethanol has the CH3, CH2 bit, which is non-polar, and then it has the OH bit, which is polar. So it's very good at combining and mixing together polar and non-polar reactants. Ethanol makes sure the KOH and the triester can mix. Ethanol makes sure they're miscible. Now, the safety precaution here is use a water bath. Don't use a Bunsen burner flame because ethanol's flammable. That's the justification. Okay, so you gently heat. Let's get to the marks.
You're still here? It's over.